Good morning, and welcome to the ATCO SpaceLab Speaker Series. My name is Kelsey Stephen. I am a member of ATCO's Transformation Team, and I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the lands that we are on today. While this is a virtual platform, I will take a moment to reflect on the meaning of place, and in doing so recognize the various traditional, ancestral, and unceded lands on which we do our business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improving my own understanding of local Indigenous peoples and their cultures. Today's lecture is a one-way video and audio format. Please ask questions using the Q&A button at the top of your screen, and we'll get to these at the end of the lecture. I will now hand it over to my colleague, Andrea Kleiber-Langen, to introduce our speaker.
Thank you, Kelsey. Thank you all for being here with us today. We're so excited to have the distinguished Dr. Robin Chhabra join us, an esteemed professor with the Department of Mechanical and Aerospace Engineering at Carleton University. Dr. Chhabra is a Canada Research Chair in Cognitive Soft Space Robotics. He received his Master's of Applied Science and PhD from the University of Toronto. He then took a position in industry where he researched the guidance, navigation, and control technologies of spaceborne systems. Dr. Chhabra's team investigates geometric mechanics, nonlinear controls, and artificial intelligence in the context of robotics. Today, Dr. Chhabra will discuss the challenges of creating collaborative networks of diverse robots across industries like manufacturing, agriculture, and space exploration. Such networks play a key role in the future of robotics. This lecture will address challenges such as modeling, perception, planning, and control, and propose solutions inspired by neuroscience, artificial intelligence, and geometric mechanics. Today's lecture has many possible applications, including rugged terrain navigation, aerial and orbital manipulation, and damage-tolerant robots. We are grateful that you are sharing your time and expertise with us, Dr. Chhabra, and we look forward to learning from you today. Over to you.
Hello, everyone. Thank you very much for having me here. Very nice introduction to the lecture. I'm honored to be here and give this lecture about intelligent autonomy of robot teams. Let me first share my screen with you guys. Just give me 1 second. Okay, can I get a confirmation if it is shared properly? Okay, perfect. Thank you so much. Okay, today's lecture is about intelligent autonomy of robot teams towards a diverse robotic ecosystem. I have divided this lecture into a couple of parts. First, I'm going to motivate the role of robot teams in the next generation industries. And then I'm going to talk about my approach in my lab, basically giving some of the results that we have obtained in my lab towards autonomy of robotic locomotion, network autonomy, and autonomy of robotic operation. And finally, I'm going to conclude this lecture with some concluding remarks. In today's era that we are living, cooperative network robotic systems are supposed to do many jobs for us. They are going to be part of our smart cities and smart agriculture, underwater inspection, search and rescue, and ultimately space exploration. To actually have robotic systems to be able to have minimal interaction with human being and being reliable in these environments, in these diverse environments, we need to actually move towards forming a diverse robotic societies. These societies, in order to enable these societies, we have to work on embodied general intelligence of robotic system and their teams. We need to address problems with the configuration and damage tolerance of robotic system. And finally, we have to work on sustainability and reproducibility of these societies. Normally, robotic the systems in these teams are performing multiple jobs such as locomotion and manipulation, and they are in the form of similar robots, homogeneous teams, or diverse robotic systems. Nowadays, in the society, we have already developed many different robotic systems, such as wheeled mobile robots, aerial and orbital manipulators, and multi-legged robotic system. And we are in the community, we are moving towards next generation of robotic system, which in my lab, we are pursuing soft robotic systems for remote sensing. Normally, these systems have to perform robotic operations in harsh and hostile environments, unstructured environments, and even unpredictable environments. That causes a lot of challenges in the guidance, navigation, and control of these type of systems. I have divided these challenges into multiple levels. These challenges can happen at the robot level, so at individual person, which is including unpredictable environments, disturbances, and damages that may occur to a robot. Or it could be at the network level, where we have to have embodied perception and reliable information sharing between different agents, and also be able to have an intelligent being to be able to manipulate and control fault and damage and anomalies that may happen in network of robots. In terms of operations, these robots must be able to perform smooth operations in an obstacle-free and contact-aware scenarios. In this talk, what I'm going to do is I'm going to go through a couple of these challenges and try to suggest some solutions for embodied intelligence of robotic locomotion and manipulation, and also adaptive, fault-tolerant localization and control of robotic teams. I have divided the first part of the talk into three main systems that we have been investigating in my lab. The first system is wheeled mobile robot, and the second one is multi-legged robotic system, and lastly, we are going to converge to a next generation soft robotic systems. In terms of wheeled mobile robots, we have been doing research on robotic systems that are suitable for all terrain environments. Wheeled mobile robots are normally designed in a way that they have a 6 degrees of freedom rigid body, which is basically the main body of the system with some payload. And it has multiple wheels in contact with the ground and rotational and steering degrees of freedom. The main purpose in my lab is to actually look at these systems from an embodied perspective, which means that we are only focusing on proprioceptive sensor information that can be collected by the robotic systems. The first problem that we are tackling here is designing a guidance navigation control for a wheeled mobile manipulator, a wheeled mobile rover that is given desired output trajectory of the system, design a control and perception module for asymptotic regulation of the trajectory while the system is robust against bounded time varying uncertainties and disturbances, optimally improving wheel traction, compensating for the wheel slips, and accurately estimating wheel slips in the system for the navigation purposes. As like other, engineering problems, we first started by looking at this problem from a naive perspective. So we have started with a very simple model of a system as a non-holonomic system. These systems have been proven that under certain conditions, they're going to be input-output linearizable, meaning that with the smart choice of control input or control transformation, we are going to be able to make the system as a double integrator. And the next challenge here is that given this desired trajectory for the system and an unknown bounded inertial and inertia uncertainties and disturbances in the system, design an optimal sliding mode controller such that the system is asymptotically stable with all observable internal states are also asymptotically stable. we have come up with a control law that consists of two parts. One part is basically controlling the system on a sliding manifold, which is designed based on linear quadratic regulation problem solving for an optimal PID controller with known convergence rate that is going to control the motion of the system on the sliding manifold. And we have also a sliding controller that is going to push the system towards this sliding manifold. And this way, we were able to accomplish a sliding mode controller for the robust control of the system. But these systems are working, or this model is actually working only when the system maintains all the non-holonomic constraints in the system, meaning that the system should always remain in a static friction regime. But we all know that we can all have slip detected in these type of systems, and we can violate this assumption. In order to improve the lifetime of this controller, we have come up with a strategy to be able to use the redundant control directions inside these rover systems to be able to optimally control the traction of these systems. These traction optimization could be formulated as follows. Let me actually bring a laser pointer. So as follows, which is basically telling us that we have divided our control input in a controller that is only changing the output of the system and a controller that is changing only the tractive forces inside the system. And by optimally designing this control part, we should be able to optimize the traction of the system and minimize the chance of moving the robot into a dynamic friction regime. And we basically are going to transform our control loop from a normal control loop into a control loop that actually includes a part that is adding these optimal control strategies into the system. In order to facilitate that, we have to first design optimal cost functions for this purpose. Normally, the cost functions that are considered for traction control are nonlinear, highly nonlinear, and they are not efficient in terms of solving optimization. We are proposing a quadratic functions in the optimizing parameters of the system. And we are also defining for the first time the notion of required force and moment at the robot center of the mass that is only dictated by the trajectory and the controller of the robot, and is completely independent of the states of the robot. So this defines a meaningful cost function, which is going to also be giving us linear optimality conditions that are easy to solve. And we also, based on this notion, we defined detecting strategies for wheel fighting phenomenon that can happen in any traction controller for robotic systems. To consider directions in the traction controller, we have divided the traction controller into two parts. We're basically measuring the steering angles, and based on our measurement, we know that if the system is in a turn or a linear motion, straight forward motion, and if it is in a straightforward motion, we only optimize the longitudinal traction of the system. And if it is turning, we first optimize the lateral traction, then go to the longitudinal traction. And if wheel fighting is happening, we are going to basically go to the suboptimal region to compute the optimal traction controller for the system. We have tested this on a 6-wheel lunar rover with lunar gravity, and many uncertainties applied to the system, such as driver motion disturbances and also wheel unbalances in the rover. And also, and we have observed particularly that the system is converging to its trajectory with a prescribed convergence time that we have designed in the controller. we are considering, we are seeing considerable improvements in terms of reducing the error at the output level of the system with a low cost of not increasing that much the control input to the system, nor the fluctuation of the control input to the system. When you're looking at the traction and improvement in traction of the system, we can actually see considerable traction improvement at high acceleration regimes of the motion. We can see the compromise between lateral and longitudinal traction at time that the rover goes onto a curve. And we also, finally, we can see that we can rescue the robot from dynamic friction regime and drifting away from its trajectory at the end of the simulation. Having said that, terra mechanics effects are not negligible. And these are going to introduce unknown slip at the wheels of any rover system. And basically effectively makes the non-holonomic constraints invalid and making the system to have making us to actually consider an alternative strategy such that we have to define a new problem that is, given the exponentially stable output tracking controller and train condition of the system, we would like to design a set of dynamic feedback transformation to compensate for these slip dynamics, as opposed to ignoring them or trying to robustly compensate for them. In that sense, we started investigating small slip dynamics in rover system, which is basically a viscous, following a viscous friction model that is coming from the linear portion of the Baker-Pachishka's magic tiger formula. We have implemented singular perturbation theory to introduce the first slow-fast Hamiltonian control system for rover systems. And in this case, we are basically turning a non-holonomic system that is evolving on a linear submanifold of the tangent bundle of the system into a system that is exponentially converging to a slow manifold, which is not linear anymore. And there's no analytical solution for that. With a very smart choice of coordinates, we have shown that these PDEs that are basically defining these invariance conditions or in this invariant manifold of the system could be recursively solved in epsilon, which is used to basically write the states of the system in a series. And this recursion in epsilon for invariance equation takes all the previous approximations of this nonlinear manifold and basically gives you the next approximation of the nonlinear manifold. Most importantly, as you can see, the control input into the next iteration of the approximation of this nonlinear manifold is going to be of order n-1, which is from the previous order. We have exploited this, this property of the new formulation that we have proposed to introduce a recursive way of doing input-output linearization for slow-fast Hamiltonian control systems for the first time. And this is basically starting from the normal input-output linearization of non-holonomic dynamics, and then we move on to find the first set of approximated transformation to linearize the first order of the series, and then we can continue this up to the nth order. And whenever we are satisfied, we can truncate this this approximation. Then we have basically replaced the input-output linearization for non-holonomic system with an nth order feedback linearization transformation into the block diagram control system for the rover systems. We have tested that on many different this approach on many different trajectories, and we have proven the uniform ultimate boundedness of the error using this approach. which basically is going to be dependent on the control gains that you're choosing and the order of approximation that we are using to be able to approximate the dynamic slip in the system. So this was about the control of these type of system, but as for the perception module, which is looking at the motion of the rover in the environment, we have been still using an ideal non-holomic velodometry, and that is not working, especially in rugged environments. So there is wheel slip, inevitable wheel slip in these type of environments, which is going to give us a wrong feedback when we are trying to have an approximation or localize the system within the environment. Visual odometry is a solution, but it is computationally expensive and not possible to work in featureless environments. So we need to design a proprioceptive sensor readings such as wheel odometry and IMU and combine them to design a multi-sensor fusion center to consistently estimate slip ratios within the system and compensate for this in the feedback loop of the system. We first realized that these systems, in these systems, steerable wheels are forming a network of sensors such that the vehicle kinematics with some conditions is going to basically give us the process model. IMU measurement is going to be our measurement model, and then based on that, we are the IMU measurement are going to give us the process model, and we are going to have some measurements of the steering angles that is going to give us the measurement model of the system. We introduce optimal sequential track-to-track fusion of steering encoders to be able to have a fused estimate of the slip estimation of the system. This optimal track-to-track fusion works based on local unscented Kalman filters that are estimating at each and every center the slip of the overall system, and also based on an optimal fusion rule that is derived as a consequence of sequential linear regression we tested the system on a Mars rover with a 6-wheel and on a path that includes high accelerations. We tested that in our software in the loop simulation that we have already seen in previous slides, and compared it with 4 other methods in 4 operating regions, which is linear with low acceleration, linear with high acceleration, transition, and in the curve, path. We have shown that the unscented Kalman filter, or in short UKF SLR fusion that we have introduced, it not only is going to improve the accuracy, but it's also faster and it's consistent when it's compared with its rivals. Now, I'm going to jump into another topic, which is on the autonomous damage recovery in legged robots. When we are actually looking at an ecosystem of robots, we have to not only look at homogeneous types of robots, we have to look at different types of the robots that can work eventually together to perform a task. One of which is multi-legged robotic systems that are good for traversing in unstructured environments. These systems also are coming with a 6 degrees of freedom main body that also carries some payload. It has several multi-degree of freedom legs that are in contact with the ground. And they have multiple redundancies that are facilitating reconfiguration of these systems, especially in damage scenarios. Especially these systems are susceptible to damage in hostile environments. And again, to facilitate embodied intelligence for these type of systems, we are focusing mainly on proprioceptive sensors in type of systems to be able to do the damage detection and damage mitigation in types of system. If I want to formalize this problem, we are given a healthy model of the system and an unknown mechanical damage in the system. And we have some recording on some preparative sensors, and in this case, IMU sensors of the system before the damage detection. And we would like to actually find a new morphology of the robot, which is somehow captured in this diagram. As you can see that within the mission, if we are detecting any damage, we go into a sleep mode of the robot. We try to identify damage and then mitigate the damage with a new gate that is designed for the system. Interestingly, when we started this research, we realized that there is no Lagrangian formalism that can formulate the full body, the whole body dynamics of these type of systems, multi-legged systems, that captures the deficient damage scenarios that we wanted to simulate for the system. We introduced the new Boltzmann-Hamel equation for global whole body dynamics of these systems that includes also leg contact dynamics and a closed loop PID controller, both in workspace and joint space of the legs. Along this path, we discovered modularity in these type of systems, or in these type of, this particular equations of motion that we derived. We could this happened because of decomposing the motion of the system or any part of the system into the motion of the main body and all the different legs in different links in the leg of the system. This decomposition is going to decompose the equations of motion, and we should be able to also extend this modularity into other structural matrices of the system, which we have already done. We further facilitate the numerical simulation of these type of systems by increasing the efficiency in terms of the timing of the simulation, by decomposing these structural matrices into a part that is including all the dynamical parameters and a part that is including all trigonometric functions. And we were able to come up with the first reconfigurable symbolic Lagrangian equation for multi-legged robotic systems. The modularity that we are talking about here is whether I can add or remove leg or links at different locations of the main body and re-derive symbolic model with no differentiation operation, which basically can be translated into enabling an online code generation for these type of systems to be able to test different scenarios in their mind. We have tested this, and the equations of motion, although they are Lagrangian equations of motion, they are faster than real time, almost by a factor of 1 to 2. And we were able to capture different damage scenarios, one of which I'm actually presenting here, which is a robot that is losing leg 2 and leg number 3 in its morphology. As you can see, then the next question or the next problem that we wanted to answer was that, okay, so now given this simulation environment, can I actually perform self-identification of the morphology of the system? But prior to that, we have to know what kind of information do we have. We only have access to an IMU sensor attached to the main body of the system. We first have to detect the anomaly and the damage in the system, and this is done by introducing a sliding window on the roll and pitch of the robot. And this is basically effectively saying that normally in a healthy condition, we would like to have minimal tumbling in the robot, but then if we actually see severe tumbling in the robot, we understand that there is something wrong in the robot. Then what we are doing is that we are defining a genetic algorithm optimization for fast self-modeling using the IMU reading in a realistic environment. A realistic environment could be an environment where we are actually recording embodied data environment that is far from the environment that we are simulating, as you can see in this video here. And then what happens is that the robot takes this data and starts basically goes into sleep mode and starts dreaming about the data that it actually acquired. So, and it tries multiple different scenarios within the robot that could happen to see such a behavior when we are using a normal gait. One of the most important things is that this identification method does not need any random motion of different links and different joints of the robot. It basically relies on the normal gait of a robot in a damage scenario. We introduced a novel fast Fourier transform filter to be able to basically compensate for the reality gap of time inconsistency with the signals. And we were able to successfully implement this to predict different types of damage scenarios. Question is that now I have the model, I have the damage scenario, how can I recover from this damage? While the system is still is in sleep mode and it's dreaming, we're using differential evolutionary algorithms to be able to optimize a new gait for the system by reconfiguring the legs and changing the gait parameters and gait patterns in the system. And this optimization is done to maximize the fast straight line motion of the system with minimal tumbling in the system. Then we perform an online gait adaptation while the robot is actually moving to compensate for the reality gap, because we know that this is all dreaming, this is all simulation, and now we are shifting everything towards the real reality. And here are multiple different gaits that we have obtained for different damage scenarios of the robot. Now, the next generation of the robot systems that we are considering in my lab are shape morphing soft remote sensor systems. Soft robotic systems are made of responsive material and flexible components. They're safe and versatile for manipulation and remote sensing in unstructured and hostile environments. They are damage tolerant, they're adaptable, they can do shape morphing and multitasking. They are coming with different shapes and different conditions. They could be tethered or untethered, and they could actually have various types of actuations and sensings. The two main categories of soft robots that we are focusing on in my lab are the shell-type soft robots and slender soft robots. The shell-type soft robots, we are basically performing everything in my lab, so from design analysis and GNC control of fully untethered amphibious hard magnetic shell-type soft robot for locomotion. And also we are looking at slender soft robot. We are looking at the design, analysis, and cognitive guidance navigation control of amphibious pneumatic modular slender soft robots in locomotion for remote sensing. Again, similar to multi-legged robotic system, when we actually started this research, we saw lack of knowledge in the literature in terms of even understanding the fundamental behaviors of these type of systems, especially on the shell type system. We have many, work on the Kostrad rods, but not much on the Kostrad shells or any shell type, modeling of the system that are fast enough to be able to capture the motion of these type of system. We introduced the new 6 degree of freedom geometric Kostrad shell for locomotion. It is based on a novel definition of deformation gradient and strain tensor, which is basically transforming everything into local coordinate frame. So all the deformations are within the local coordinate frame in the original shape of the system and after deformation. We derived strong and weak forms of static and dynamic equations using symmetric Lagrangians and isotropic constitutive equation on special Euclidean group. And we have also added magnetic effects as body twists on Koszorot shells in order to complete our analysis for all shell type designs. To solve these equations numerically, we have introduced a total Lagrangian finite element method, which uses 4 Gauss points for spatial integration, and also a novel Newmark method on special Euclidean group for time integration. The method is going to be singularity free in terms of dynamical analysis. It is simple and it's fast for analysis of different types of robotic locomotions. And it's ideal for the design and shape morphing and designing guidance navigation control for these type of systems. We have already tested or validated the equations using a hard magnetic elastic plate, which is a blending mold star 3,1T and neodymium iron boron permanent magnet, which is solved inside a silicon shell type plate and magnetized with 1 Tesla external field. Then we actually looked at it in different types of bending conditions, and we validated our equations that we have obtained here. And we tested that, or we have implemented that to introduce soft magnetic grippers for variable shape object grasping, as you can see in the videos. And we have also extended the result to actually introduce contact dynamics in these type of shells when they are sliding on a surface. And you will see momentarily why we were investigating this type of phenomena. And this is our robot. So this is the first prototype of our robot. It's the first fully untethered amphibious magnetic robot that can work in different modes of operation. It can actually walk in a walking mode. It can turn by changing the location of the magnetic fields. It can actually have motion with very high frequency. And it also can swim. Everything about this robot is built in my lab. We started with molded curved shell with embedded hard permanent magnets. 3D printed all the rigid parts of the system. Currently, the gate is impulsive, and we are working towards introducing intelligent embedded guidance embodied guidance navigation and control system for both walking and swimming of this type of robot. Next question that we tackled was slender soft robots in locomotion. Although there is a lot of literature on Koszorot rods, but there is not much literature on Koszorot rods when they are in locomotion, such as worm motion of a Koszorot rod. We use the principal bundle configuration space of Koszorot rods using special Euclidean space as the rigid motion of the system, the rigid part of the configuration, and strain space as the flexible part of the configuration. And using parameterized strains, we were able to introduce the first Lagrange-Poincare equation for soft robotic system that effectively divides the momentum of the center of mass into 2 momentums. One is purely rigid motion of the center of mass, and the second one is dependent on the actual flexible motion of the system. Through a formal variation of calculus on Lie groups, which is already validated, we were able to introduce singularity-free equations of motion that is independent of the rigid pose of the system altogether. And it is explicitly the whole dynamical equation is divided into elastic and rigid decomposition of the system, of the equations of motion, of system of equations. We have already introduced contact dynamics. The tangential forces are defined based on Coulomb friction, and the normal forces are basically solved through Lagrange multipliers and implemented into the model of the system. The robots that we are interested in are worm-type robot, and we are looking at next generation inchworm locomotion of Koszorot rods. We have already come up with the design, and we are right now at the prototyping and building the first prototype of the design. That actually includes multiple segments, pneumatically actuated soft robot worm. It has 3 chambers. In each segment, it has 3 degrees of freedom actuation. And we have already developed some shape morphing strategies based on spiking neural network perception and model predictive control of the Koszorot model using a finite number of actuations and intrinsic shape error functions in the system. The first prototype that we built was a 1 degree of freedom proof of concept was a 1 degree of freedom worm that is locomoting only 1 degree of freedom, and we are in the process of building the full 3 degree of freedom modular worm shape robot. Now that we have seen different types of robotic system that we are involved in my lab, I want to talk about some strategies about adaptive fault tolerant control of robotic teams. So we actually tackled this first from the homogeneous robot network perspective. So we actually consider N robots that are following a virtual leader, and all of them are moving in SEM, which is generalization of spatial Euclidean space, and receiving control forces and moments at their center of masses. Each of them is equipped with a local intelligent guidance, navigation, and control. And the problem that we are tackling is that given a formation which is basically some relative poses, that the defining differences between these, differences between the poses of these systems with respect to the leader, how can I find a neural network-based controller to make and keep the formation with bounded disturbances applied to the system, unknown dynamics of the system, and also actuator faults in the system. Each robot can only access its own states and the virtual leader's states. Again, towards the fact that every robot is only seeing, whatever it's available to it. So it's a distributed control perspective. We have translated this problem into a local trajectory tracking problems that includes the aerokinematics, which has the relative velocity twist and also relative pose error that must be measured by a navigation module, which is the topic of my talk in the next couple of slides. And then the aerodynamics is going to include unknown dynamics of the systems, loss of efficiency in the actuators of the system, and also unknown disturbances within the system. We have introduced a distributed control law based on neural network on Lie groups without parameterization of the Lie group. It is the learning rule that we have come up with is Lie group compatible. It's singularity free and global. And we're using the damped gradient descent of a model reference cost function. And we have shown globally ultimately boundedness of the control under regular condition. We have tested that for 3 robots moving in spatial Euclidean, the 3D spatial Euclidean group with unknown inertia, unknown gravity, 50% loss of actuation effectiveness in the robots, and periodic and constant disturbance applied to robot. And as you can see in the picture, there is a comparison between the neural network control and the normal PD control applied to the system. you can see the configuration error and the velocity error of the system, which shows drastic improvement in the performance of the system. But these, as I mentioned, these robots, first, they have to have a perception of their location. So they have to have a correct feedback about the pose error and the twist error, velocity twist error in the system. Now, the problem of localization, here we define the fault tolerant multi-robot, multimodal localization for the team of the robots. The problem is that given a group of N robots equipped with inertial velocity and pose measurements, and they have proper way of communication between different robots, how can I design a distributed localization system with N local extended Kalman filters on Lie groups? We first have to develop stochastic correlated configuration operations on matrix Lie group to be able to answer this question, because this is going to appear over and over in the development of this strategy. We first introduced configuration operations such as inverse composition, averaging, differencing, and also fusion between different elements of a matrix Lie group. We introduced a novel Lie group, G of X, for process model, which includes inertial measurement considering biases for the first time as a stochastic phenomena within the sensor model. And also have a novel Lie group, G of Z, which is basically the measurement model, which includes both velocity and pose measurement as the measurement model. The fault detection module is happening based on Mahalanobis distance metric. And based on the category of the robots, whether they are leader or follower, based on and with different capabilities, we have introduced 3 different types of a multi-robot, multimodal localization. The first type is basically uses the IMU as the prediction stage, and each robot is assumed to actually be equipped with a camera that can detect a marker to give the pseudo pose of the robot with respect to either other robots or with respect to a stationary marker. So for the leader part, leader is only able to detect a stationary marker. So it basically takes the IMU as a prediction and then checks if the marker is available. If it is available, then it actually includes this in the estimation or localization of the leader. If it's not, then it's only going to rely on the odometry reading of the robot. For a follower, either a follower can see only the leader, or the follower can see the leader and another follower. So if the follower can only see the leader, then it's going to basically update its prediction based on IMU. And then if the marker is available from the leader and the estimation of the leader is available, then it's going to perform, combine that with the odometry reading and update the odometry and the marker. Or if not, then only the odometry is going to be used as the measurement model. And then lastly, if a follower can also see another follower, they actually can get an estimation from the follower too, and combine these 2 estimations. That is, one is coming from the leader, the other one is coming from the follower, to be able to have a precise estimation of the follower in a robotic team. We have already experimented this, and all rovers are equipped in this experiment. As you can see, we are using the LIMO rover by Indra Robotics. We have a system of 3 of these rovers in my lab, and each rover is equipped with an IMU wheel odometry camera to track fiducial markers. Leader can only see a marker on the ceiling, and all the rovers carry markers at their backs to be able to be identifiable by other agents. In this experiment, we tested on, which is tested on 4-wheel indoor rovers. we can see uncertainty propagation, which is expected from leader to follower 1 to follower 2. You can see recovery of the ground truth by the fault-tolerant multimodal localization framework that we are proposing here. You can see that IMU and velodometry, especially for the follower number 2, they are completely failing, and you cannot get any meaningful information about from them. And you can also see the improvements that we can achieve with addition of the fault-tolerant control that is added to the system. When all of these rovers or the robots are at their position, they have to perform an operation. And normally this operation is done through a manipulator that is mounted on the robot. And this brings us to the another problem, which is vehicle manipulator systems for manipulating especially uncooperative objects. That's the main topic that we are trying to address in my lab. One of the applications of that would be on-orbit servicing or debris mitigation in space. It could also be undersea vehicles that are manipulating objects, or even aerial manipulations. Every vehicle manipulator system comes with a multi-degree of freedom manipulator, and also a 6 degree of freedom rigid base and a 6 degree of freedom rigid target. Almost zero gravity environment is assumed in this research because we are mostly focused on space applications. We assume no active control at the base, and we are assuming that we get the target pose estimation through some cameras. The problem that we are trying to solve is called safe manipulation. We want to design guidance, navigation, and control modules that regulate the relative pose between the end effector and the frame on the target in preparation for capture, while improving manipulability, avoiding workspace and kinematic and dynamic singularities, preventing self and target collision, remaining functional even if the target is out of reach of the system, and accurately estimating target pose and velocity. We start with the dynamical equations of motion of these type of systems. These systems are revolving on principal bundles, which includes a special Euclidean group and the internal degrees of freedom of the robot, which is basically the arm degrees of freedom. Without any base parameterization, we derive the equations of motion, which are leading to the first singularity-free equations of motion, which are called Lagrange Poincare equations of motion. These are basically giving us explicit internal external decomposition of the dynamical equations, and they actually give us an equivalent fixed space manipulator dynamics that we can easily design control laws for, and they're effective in control design and hardware in the loop simulations. Now, we are dividing this large problem into some sub-problems. The first sub-problem that we are tackling is regulating controller. So given conserved momenta in the system, what we want to do, we want to design a control that regulates the relative pose of the end effector and the targets that guarantee internal stability and improves manipulability of the system. We're performing geometric feedback linearization on the Lie algebra of the special Euclidean group. End effector is considered as body 0 here because of the computational efficiency and minimal computation of Jacobians that are needed in the control law. Velocity error in the end effector is computed, and by taking the derivative of that, we actually find a feedback transformation with some feed-forward terms that can cancel all the nonlinearities of the system and linearize the system on the special Euclidean group. This UTC-TS, which is the U of task space, the control input of the task space, our new control input now. We design a geometric PID control using an intrinsic error function on special Euclidean group, and we decompose the system into workspace and null space through this transformation by introducing the null space parameters as new. Now, by setting the null space control as following, we are able to fully linearize the whole system and then basically have a direct control over the task space motion of the system and null space motion of the system. And by introducing the null space control input as UNU and UM, we are able to stabilize the null space motion of the system and effectively improve the manipulability of the system. W here is basically a measure of manipulability for such systems. Now, the next question is that this is going to only work, this output tracking control is going to only work within the workspace of the system. So wherever the system goes into singularity, there are some Jacobian inverses that I have to compute that are going to go ill-conditioned, and it's going to explode the whole system. What can I do? I can design minimally invasive additive guidance modules that basically stop the motion in the direction of decreasing manipulability of the system when the system is approaching an inevitable singularity within the workspace or out of the boundaries of the workspace of the system. And it also pushes the manipulator and its joints away from obstacles within the system. This control law must be Lipschitz continuous and effective as an interest region of interest, not everywhere to basically interfere with the actual manipulation work of the robot. We introduced the following potential function for this design. For the singularity avoidance, we are basically killing all the workspace control efforts in the direction of the gradient of the change of the manipulability of the system when it's close to a singularity phenomenon. And basically, effectively, if you look at the problem, it's basically following a shadow of the target within its own workspace. The manipulator is following a shadow of the target within its own workspace. And so basically, virtual end effector body wrenches are exploding at W equal to 0, and we are able to introduce the following combination of the PID controller and the singularity avoiding control law. For obstacle avoidance, we do the same thing. This time, we actually add the obstacle avoidance control input within the null space of the system, and we only activate the obstacle avoidance action at the task space of the system whenever we can see that the obstacle contact is inevitable with the robot. As you can see, the full safe critical control of the system could actually be divided into the PID controller, singularity avoidance, and obstacle avoidance, inevitable obstacle avoidance in the task space of the robot. And in the null space of the robot, we are stabilizing the internal dynamics of the system, improving manipulability, and performing obstacle avoidance. And UTS and UNS are completely decoupled, and we can decouple. We can design them completely separately. But if we actually want to follow an object, we should have an estimation of the location and the velocity of this object. How can we obtain this? Now, given a base manipulator states and also only pose measurements from two cameras, one at the wrist of the manipulator and the other one is at the base of the manipulator, we would like to find an accurate target pose and find accurate target velocity. Tackle this problem, we actually look at invariant extended Kalman filters on special Euclidean group to filter noise out of the measurements that are coming from the cameras. The process model is based on the conservation of momentum, and the measurement model is basically the pseudo poses that we are capturing from these two cameras. Then we introduce a recursion for pose estimation of each of these cameras based on an extended Kalman filter to compute cross-covariance estimation between these two cameras and fuse the correlated pose the correlated pose estimates on a spatial Euclidean group, with introducing the first analytic solution to actually the following minimization problem for the estimation of the pose of the object. In order to have a better estimation of the velocity of the object, we basically combine the fused estimate by the conservation of momentum equation of the object to be able to get a better estimate of the velocity of the object. We have put everything together and tested it on several scenarios, and this is one of the scenarios that we have tested. As you can see that within the workspace of the robot follows the target goes out of the reach, the robot stays and waiting for the target to come back. Target comes back, and at this moment the robot performs some obstacle avoidance maneuver to be able to clear its base. Another problem that we have tackled in my lab was about safe planning of these type of systems. So what if the object is moving very fast and its motion is complete and its dynamic is completely unknown? How can I actually have a trajectory that is generated to be able to capture this object? The problem is this: given conserved vehicle manipulator, geometry of the target, only having access to the noisy estimates of the target pose and the manipulator joint angles and velocities, and uncertain system parameters, find the joint velocities trajectories for the manipulator such that the end effector follows randomly moving target, avoiding collision with the manipulator and the target, and respect the joint and end effector limits. We introduced the first deep reinforcement learning for safe planning using deep deterministic policy grading method, which is an actor-critic agent. We first divide the problem into 5 sub-problems, and we perform transfer learning in order to go from to learn the simplest task all the way to the most difficult task. And through this transfer learning, we are basically transferring the weights of the critics only. Multi-critic is applied in this strategy to separate the 2 objectives of following an object and doing obstacle avoidance, which showed very successful in this problem. We also perform introduce priority episode sampling to guide the search within the optimal policy of the system. They perform the learning performance. We have tested the learning performance on a two-link space manipulator system, and we compared performance criteria in terms of running average total reward. As you can see, that trajectory generator with and without priority sampling, as you can see that the DDPG with the priority sampling is performing much better than the original DDPG. For obstacle avoidance, we're using double critics, and you can see the superior performance of the proposed method versus the original DDPG. And we have also tested the original DDPG with giving it extended time to be trained versus our limited time of training using our own methodology, which again outperforms the original DDPG. And here are some of the trajectories that were generated by the system to be able to safely capture. The red dot is basically the capture point, and the green circle is basically the obstacle. And the capture point is attached to the obstacle, and this is basically resembling the fact that you're trying to, for example, capture a satellite, but you don't want to hit the satellite. To conclude my talk, first I want to reaffirm the fact that in our today's life, we need to actually move towards a diverse robotic ecosystem. And the path of this diverse robotic ecosystem passes through embodied general intelligence, which comes with self and environmental consciousness, intelligent perception, learning, planning, and cognition. adaptability and computational efficiency, and one of the neglected parts, which is fast, reconfigurable, and global models of the system. Without models, we are not going to be able to do any planning. We are not going to be able to do any learning in these type of systems. The approach that we have taken is a hierarchical approach. We first look at the robots in locomotion, so individual robots. We introduce resilient autonomy for wheeled mobile robots. We introduce self-consciousness and damage recovery in multi-legged robots. And we finally introduce design and fabrication of shape morphing systems, soft systems. We have also looked into adaptable and fault-tolerant neural network perception and control for robot teams. And we concluded this talk by looking at safe autonomy for vehicle manipulator system in operation in proximity of different types of targets. Some of the existing works in my lab include biologically inspired embodied cognition for intelligence, which includes spiking neural networks and using neural engineer framework for end-to-end neuromorphic guidance navigation control for robotic systems. We want to use vector symbolic architecture for cognition and basically showing the interplay between mind, brain, and body within a robotic system to perform embodied learning in these type of systems. And we would like to eventually implement everything on a neuromorphic hardware in the system. Another point of focus in my lab is long-term learning-based guidance, navigation, and control of the systems based on actor-critic model predictive control, model-based expert and simulation to real transfer learning, and also exploiting environmental and intelligent planning at different types of operation. And finally, we are looking at embodied decentralized collaborative manipulation between different robotic systems to show fully embodied body mapping and the robot's morphology, and also collaborative manipulation planning and decentralized low-level planning and control of these type of systems. Altogether, I would like to thank everybody in my research lab who contributed to several, to all of the topics that I have presented today. And I give the floor to the moderator.
Well, thank you so much, Dr. Chhabra, for the wonderful lecture. You may now stop sharing your slides if you'd like. And for everyone that's joined online, we're going to move into the Q&A portion of today's session. So there aren't any questions yet, but I do have a question. I'm going to check my notes so I make sure I get this all right. But we talked about many different kinds of robots today, and the ones that really interested me were the adaptive fault-tolerant robots, so the ones with the multi-legged robots that were able to go into the dreaming mode and kind of reconfigure themselves. And just at the end, you had kind of also mentioned collaborative manipulation. And so I'm really interested to know if you've done any research or you plan to do any research on like teams of robots being able to manipulate parts like together. So for instance, one robot who's healthy goes to help out a robot that might be damaged.
Thank you very much for the question. Yes, the ultimate goal of the research is exactly what you mentioned. I am in the process of doing some research on embodied decentralized collaborative manipulations for robotic systems. And the main idea here is that all bodies are going to be able to individually map and model themselves, such as the one that you've seen in the case of the multi-legged robotic systems, and try to compensate for any deficiencies that they only have themselves. And in the planning module, we are expected to actually see some mitigation strategies to be able to compensate for the damaged robot in a team of the robots. The short answer to your question is that we don't have results to show you. Otherwise, I have shown you. But this is exactly the direction that the lab is going.
Great, thank you. That's awesome. And our first question in the chat comes from Robert, who asks, is there a particular reason for using a neural network for controlling robots and teams instead of an optimization approach?
The only reason that I can actually talk about is that the way that we are looking at the system. We basically are looking at these type of systems as, especially for soft robotic systems, as bio-inspired systems. So we are basically trying to explore two characteristics in these type of systems. Biologically systems, we have softness of the tissue to give immense amount of adaptability of these type of systems, shape morphing, and being able to perform multiple tasks. And they're efficient information communication within the body of the system, which is through neural networks. We started with artificial neural networks, as you saw in my lecture, but we are moving towards spiking neural networks. And this was basically the first step towards that goal of, can I actually have spiking neural and neuromorphic, completely end-to-end neuromorphic guidance navigation control system for a soft robotic system. So that's the end goal of this research. The reason that we are not using optimization is not that the optimizations are not good. Optimizations are perfect. The reason is completely different. We're trying to look at biologically inspired ways of improving the adaptability and performance of these type of systems. And that's the angle that we are looking at the systems.
Great,
I hope I answered
so much.
the question.
Yeah, great, thank you. That's amazing. We don't have any other questions yet. I'll maybe give it 10 more seconds for people to get any remaining questions in. So for anyone that's joined online, if there's anything you'd like to ask Dr. Chhabra, please add it to the Q&A chat at the top of your screen. While we're waiting, I do have one more question. When we were talking about small slip dynamics
Yes.
and kind of perception modules, you mentioned that the visual odometer is computationally expensive and not possible to use in featureless areas. I was wondering if you could maybe share some reasons why it wouldn't work in featureless areas, and if there is an alternative solution that works better for a featureless area.
Example that I had in mind was a lunar surface. So on lunar surface, basically we are talking about only sands on the ground, and there are points of motion, or the times of motion, that the system is going to move inside the dark side of the moon. So in these type of scenarios, visual odometry is going to fail. If we want to actually perform any visual odometry, we have to have a stationary object that you pin our attention to that object, and based on the detection of my distance to that object, I'm going to have some perception about, okay, so I know where that object is, I know where I am located with respect to that object, so I know where I am. But if there's no object over there, everywhere looks the same, so then how can you actually even use visual odometry? So that's exactly the place that it would fail. In the lighting condition, in the terms of lighting condition, as I mentioned, for example, in the dark side of the moon, there's no way that we can actually use visual odometry. We can use lidars, for example, or different types of radars to be able to detect objects, but if there is any object. So that's what I meant by featureless, areas. At the same time, we have to keep this in mind that this is a very expensive way of computing or localization. Although we are also doing it in my lab. I mean, we are using cameras and markers to be able to accomplish this task. But the way that we are looking at the problem is slightly different. You're, for example, looking at a team of the robots, that the first robot has a special, capabilities of observing the environment. As I mentioned, for example, my first robot, the leader of the 3 robots, the rovers, is going to look at the ceiling. So it's going to get some idea about, for example, if we are looking at this, let's say on the surface of another planet, you're gazing stars. So you're having stargazer on the, leader of your system that can give you a sort of global understanding about where you're located on that planet. But not all of the rovers have the same capability. So we're trying to break down this idea of visual odometry into multiple, ways of making system, better perform in featureless, environments. So then the leader has a better idea about its global position, and then the followers are seeing the leader, then they have something to follow. So you have a feature there existing there, that's your leader, and you start following, and you get a better localization over the whole team of the robot. So that's the philosophy behind this.
Amazing. Yeah, thank you for the information. That's very helpful. Our next question in the chat comes from Mary, and Mary asks, did you watch Worms to get the motion for the tube robots?
Yes, we did. We have a lot of videos of that. Yes. So the worm locomotion, although it hasn't, the robot it's in manufacturing for fabrication stage right now. We already have 1 module of the robot with 3 degrees of freedom. We have already tested that. We haven't assembled all 3 of them to get the full motion. So it hasn't been tested yet. But in simulations, we have already looked at that, and we have already watched a lot of videos of the inchworm motion of the worm. But the idea is beyond that. We are looking at not only locomotion, but we are looking at obstacle mitigation. We are looking at crawling over stairs. We are looking at scenarios that normal, I would call it normal, or today's intelligence is not going to be capable of doing it unless you actually feed it extra information. So for example, for a robot, if you do not define what an obstacle is, the robot does have no idea if it faces an obstacle that is basically blocking its way to move forward, unless you already define the concept of obstacle for the robot. What we are trying to do by the whole idea of embodied intelligence in these type of systems, we don't even want to define concept for the systems. Systems must be able to have an understanding about their capabilities, their own limitations, and the limitations of the environment by probing the environment. So this is the end goal of the system, not only locomote, but also be able to define, not find, define something as an obstacle and try to mitigate that obstacle.
Amazing. Thank you, Dr. Chhabra. We have another question. My apologies if I say your name incorrectly, but it's Bahadur, who asks, thanks for the great presentation. I was just wondering, how do you think RL and robotics would help motion planning compared to old techniques, control algorithms like MPC?
I see a lot of similarities between MPC and RL. To be honest with you, in terms of optimization procedure, they are very, very similar. The only difference that the only fundamental difference that I can say is that MPC always looks forward to plan. So it's planning forward. Optimization is being done forward. With an assumption on the model of the system, you are basically planning forward ahead of time. As opposed to reinforcement learning, where you actually look backward. You look at your experiences and whatever you've learned from those experiences, and you're not using a model. So that's the fundamental difference between the two approaches. Both approaches can work in different types of scenarios. And what we are suggesting in my lab is a combination of the two. We are looking at a scenario where we can actually use model predictive control for short-term planning of the robots, and looking at reinforcement learning for long-term planning. Long-term planning could be done in a simulation platform, and the knowledge could be shared by the robot. And then when the robot is in the environment and performing a task, they're basically doing MPC, model predictive control, to be able to plan for their motions.
Thank you so much. We have another question from Amar, who asks, what could be and are some trade-offs between centralized or leader-based and decentralized control architectures for robot teams?
Thank you very much for the question. That's a very good question. The first obstacle, I would say, one, robustness. Centralized systems, centralized planning is based on a lot of information that is coming from the different types of the robots to a central computer to be able to perform the planning. That is basically limiting the amount of communication. This is basically extending the amount of communication that must be done between the robots and the center that is planning, the planning center. The second thing is scalability. So this high amount of communication causes a lot of numerical inefficiency in the centralized approaches. Second thing is, as I mentioned, is the what was I saying? Sorry, I just forgot what I was saying. The scalability, yes. The second term is scalability. Obviously, because of the number of communication links that we need and the amount of computation that we have to do at the center, at the central planning system, we do not have enough resource to have, let's say, 1,000 robots. We can only accommodate several, a handful number of robots. So scalability is under question. And lastly, robustness of the system. If we do not have a distributed system that can individually, each robot can have an embodied interaction and experience with its own environment, has a good perception of itself and its environment and all the other companions, we are not going to be able to accommodate these type of systems or team of robotic systems in a critical situation, a situation where we actually have fault in the system, where we actually have damage in the robots in the system that are unseen for the robots. So these are all calling for having local computation centers on the robot, which are only relying on the partial observations of the robot, not even full observation of the robot. You're not even, I think knowledge sharing should not be even done, but the partial observation of the robot equipped with inference engines that are capable of deducing different complex scenarios and analyzing different complex scenarios to deduce the best action to be done in those kind of critical scenarios. So if you want to have robustness, we have to go with distributed. If you want to minimize the computation and communication, we have to go with the distributed. And if we want to have a scalability in the system, we have to go with the distributed ones. But one thing that the central planning systems are very good at is, yes, if the whole system is working perfectly in the lab, I know the number of my robots, I know my lab environment, and everything works perfectly, like a manufacturing facility. Everything works like a clock, okay? I never go with a distributed, control system for that type of facility. I definitely go with a centralized one. But now consider the first picture that I showed in my presentation. Consider a team of the robots from different, types are collaborating on the surface of the Mars without having any, human intervention. So in these type of systems, we cannot rely on central computation systems for doing all the planning and control of the system.
Thank you so much, Dr. Chhabra. Our last question of the day comes from Alida, who asks, what inspired you to pursue research in this field?
So thanks for the question. I would say my curiosity about intelligence. So the most inspiring thing I would say around me is all questions that I have had all the time about intelligence. The first question that took me to this field was that what is intelligence? And still I don't have the answer to that. And I'm going to do research until the time that I have at least a partial answer to that.
Amazing. Thank you so much, Dr. Chhabra, for your amazing lecture and for all your answers to our questions. That is the end of our event today. Thank you, everyone who joined us online. We're glad to see some familiar faces joining us again. If you're interested in watching more of our previous lectures, they are available on ATCO's YouTube channel. And with that, I'll send you all off to enjoy the rest of the afternoon. Thank you so much for joining us, and we'll see you next time.
Thanks for having me. Take care.